Okay, yeah, maybe I'll start today's lecture. So, this is week 8 for RL of NPTEL-SWAYAM live session, doubt clearing session. So, first yeah, if you guys have any doubts, you can ask me anytime in the middle. So, first I'll do a recap on what was done in this week's lecture. So, this week's lecture first started with functional approximation. So where so what we usually do is we try to find the value of each and every state. So this is what we are trying to. So this is an estimate of the value function. This is the true value function. We always try to estimate the value function of a state by using the Gell-Mann operators and all those kind of things. So in functional approximation, what we do is we parameterize the value function with thetas, and now you have so now you want the parameterized value function to be as close to the true value function which is given. So so I think sir looked into one of the special case where it was a linear functional approximation. Okay, so okay, so first let me give you an example of maybe a small example problem of how functional approximation and all those works. So yeah, so but before that let me just define what all needs to be defined and all. Okay, so yeah, so this is a feature vector, so which belongs to every state will have a feature vector, and it will be of d-dimensional feature. So I when I set up the problem, I'll give you intuition of what the feature vector is, but there is a feature vector for linear functional approximation. This I'm taking for linear functional approximation. So what I want is this feature vector into my parameter my parameter theta should be as close as my v function, so with some policy or some value function. So this should be as close as my v. This is what I am trying to do. Yeah, so this is my final setup. So okay, what is d, what is okay, so cardinality of S is the number of states you have, and cardinality of S is very large than D, the feature vector which each state requires to represent. So yeah, so maybe I'll start with a small example problem that will make everything clear. So you have two places, A and B, and you have a route in between them. There are cycles in both the places. So there is a cycle. Okay, so this is a okay. I don't know if you guys have seen this type of cycle, but you know that you can rent bikes or cycles from point A and go to point B and drop it off at point B for traveling and stuff. So this is a problem based on that. So suppose you have, so there is a company called some X or something. The company has some cycles. It has two stations, A and B. So it has some number of cycles in A, some number of cycles on B. So if you are a customer, you come to that location, you log in through X, you pay some fixed amount of money to the company X, and then you you take the cycle and you travel it to B and you place it and you leave it and you go and do it. Someone who wants to go from B to A can come, pay some amount of money to company X, take the cycle and go to station A and leave it there.
So, the person who is picking cycle from place A,
Yeah.
can't he or she place it back on the section place A?
Yeah, if he is like, if he wants to go to B and then again come back, like if he has some work at B and he is not planning to come back, like he wants to, like A might be where he's staying, B might be his office. So morning he'll take a cycle from A, he'll go to B, he'll leave the cycle there, and then he'll go to his work.
Got it.
He when he wants to go back, he need not take the same cycle again. He can again come to B, and if there is cycle, he'll book that cycle and he'll come back to B. So the same cycle might not be booked for the whole. That will be lost for the company. Right? The cycle will be waiting at point B for the whole duration from morning to evening. So they just want one-way booking.
So if a person takes cycle for the rent, so until he put it back, cycle is his or hers. Like,
Yeah, so the amount of money he will pay is for his trip from A to B. That's it. Once he reaches B, he'll put back the cycle there. So that amount of money. If he wants to go from B to A, then he has to pay extra to go from B to A.
I got the question actually.
Yeah. Okay. So now, no, actually so this is the setup, the problem setup, the environment. This is the environment. The problem is at 12 midnight, the company does not allow any more taking away of the cycles from A to B or B. At 12 midnight they stop. At 12 midnight what they do is they have like suppose at 12 midnight there were 3 cycles here and 2 cycles here. Do they want to keep it that way, or do they want to make some changes in this so that next day when again the renting of cycle starts, they don't have have a situation where customer comes and finds no cycle at his place. So it could be that at 12 midnight all the cycles were placed here and there are no cycles here. But if so now do you want to change this configuration? What is the optimal configuration so that no customer the next day gets left out without any cycle for traveling? So now, but there is a cost, some cost involved for the company to just transfer the amount of cycles that from A to B. So could anyone tell what one of the feature vector of a state could be? Okay, suppose there are 5 cycles that company X holds. So what is one possible feature state that
so if the one possible feature can be the question is how what is the one possible feature that minimize cost
no,
of
yeah, it did not minimize cost or something, but what could one feature be? But one possible features of state B. So X could have like some 1,000 cycles. So what could one feature of X be? Let us keep it 5. Okay, so let me give the answer. So one possible is not the answer, it could be anything, it could be number of them. So it could be number of cycles in U and number of cycles in B. So at midnight, the state could be like 5-0 or 1-4 or 4-1, like anything, it could be anything. So this is one way of representing states for our problem. So yeah, so could anyone tell what the 5 feature metrics would be? Okay, I have not yet gone through the feature metrics, but I think if you have gone through these classes, you would have understood the feature metrics. Like there is a feature vector for each state, and you put all the feature vectors in the row, you get a feature matrix. So this feature matrix would just be 5 0 1 4 2 3 3 2 4 1 0 5, something of this sort. And now you want to find theta such that, okay, so now you have how many states here? Yeah. So here the states could be so these are all your states. So 1 2 3 4 5 6 states. So, and I'm missing some object. 6 states. So you want to find a theta, a vector theta, such that this gives you your value function for each state. So it gives you value and value function. This value function belongs to a vector in S. So you will get V of state 1, V of state 2, V of state 3, V of state 4, and V of state 6. So you want a theta such that you can parameterize the values of each state into a linear function. Okay, is this clear, or do you guys have any doubt on this?
So clear.
So yeah, so this is just one example of what we're trying to do. So now I'll just do what sir has tried to do in the class. So I'll denote an error function. I don't think sir has denoted as an error function, but it is the least means per error, I think. So one thing you could do is you could minimize the expected value of d mu s minus phi transpose s into theta whole square. Stick to sir's notation. It's ps minus phi transpose s dot theta whole square. Yeah, so this is the least square error function. So we try to find the minimum of this error over all theta. So I need to find a theta such that this term gets minimized. Okay, so technically what we're trying to do is, so we have a set of 5 thetas, right, such that thetas belongs to Rd. So this is my whole theta space. We define a theta space where I have multiple thetas. Like thetas could be anything, any vector, or it could be reals, or here it is Rd. So I have a whole space where I have these thetas. Now my value function could be anything. So now I want to find one theta which is closest to the value function. So this is an equation of a plane in Rb. This is an equation of a plane. So yeah, so what this gives is, I take any theta, I get a line in this plane. So now, suppose this is the origin, and I have a value function at this point, which is not on the state. So what I want is, I want the optimal, which is the closest. The closest would be the projection, perpendicular projection to that plane, to this plane, this linear plane. So I want this, the theta which gives me this vector. These all I hope sir has covered in class. Yeah, but this is one way of doing functional approximation. Okay, why we are doing this, I'll come to that shortly. But this is what we're doing. And then, yeah. So yeah, then sir did one more thing of yeah. So next in the same recap, I want to say that this expectation, you need not do an expectation. You could do a weighted average for errors. So how do you weight the errors is, because you have an underlying MDP, you can see at uh, what state has high probability of going there, and then you can weight according to the probabilities that the state would take. Okay, so you guys have you guys know what stationary distribution and invariant distributions are for a Markov chain?
No.
Okay, so let me give you a very brief things of Markov chains for stationary distribution and stationary invariant distribution. I hope till this part is clear. I'll just explain Markov chains because I need to explain why you need to weight uh, this error, because there might, okay, you might have okay, first I'll give the intuition. So you might have a problem which has some million number of states, right? So when you have a problem with million number of states, some states you are very with probability say point not one, you reach, like you visit that state with very less probability. Then why do you want to calculate? So suppose now if you're calculating a value function, you want to weigh that state, the value function of that state, very less probability, because you don't care how the value function is at that state, because the probability of going there is very less. That is how your environment is different. So you could take it like in chess, some very odd pathological cases where that kind of state would never happen. So like, or the probability of it happening is very less. Okay, maybe one probable state in chess is your states in chess, playing chess, are your the locations of all the players. So one state could be where if black started on one side of the board, white side on the other side of the board, just flip it, like just flipping it, like it's the same thing again flipping back. Going to that kind of state is very improbable. I'm sure it might happen, but going to some of the state is very improbable. And so why do you want a value function which gives me which calculates the value of that state, which is very less probable? So that's why you weigh the average. Is the intuition clear? Why I am going for weighted average?
Yes.
So Markov chains. So before going to Markov chains, you understand the MDP setting, right? So you have state, you have action, you go to another state with some probability.
Yeah.
So Markov chains are similar to MDP, but way more similar. So what we have is, we have states and transition probability transition matrix. That's it. No actions. So let me give you an example. 1, 2. No actions. So the environment is doing everything. There is no action involved. So if you are in state 1, so one setting could be, okay, I'll make it V11, V12, V21, V22. So this is a two-state Markov chain. Okay, so I'll just give you. So Markov chains could be discrete time Markov chain, continuous time Markov chain. Okay, when I say Markov chain, it means that the state space is discrete. Okay, when I mean discrete time, so at each discrete event of time, a transition from one state to another takes place automatically, without any action, without you giving any action. Markov chain, again discrete state space. Continuous time means, okay, continuous time is a bit different, but I'll give you the main point here is that it waits for an exponential amount of time. So what you do is, you run a clock. Suppose it's in state 1. State 1 will have exponential distribution, right? Will have a clock behind it, like okay, so it will wait for mu1 time, where mu1 is distributed exponentially with parameter mu1. So it will wait for time t1, which is exponentially distributed with parameter mu1, and then based on the DTMC probability matrix, it will shift to 2. Once it has state 2, it will wait for time t2 with exponential distribution parameter mu. Is this clear? DTMC and CTMC.
Yes.
So, continuous state space, I am not going into it now. It's a bit difficult, but let's stick to DTMC. Let's stick DTMC, not even CTMC, DTMC. So in DTMC, what happens is, so now you get a transition matrix. So you can write the transition matrix as P11, P12, P21, P22. Okay, and then suppose initially you always choose 1. You always start at 1. That means at time t equal to 0, how is the distribution, initial distribution? What is the probability? This is a probability function which tells you how it is distributed. So suppose I say at time equal to t, start at 1. So what would pi 0 be?
Because we are starting from 1.
Yes, it will be 1, but not because we are starting from 1. Well, it will not be 1, it is a vector. So what is pi 0 is? Pi 0 is a PMF, probability mass function, which tells you the probability that you are at 1 at time t equal to 0, and also probability that you are at time 2 at t equal to 0. So what is the probability that you are at time 1 at t equal to 0? One, 0. I hope you've seen this.
Yeah. Right.
So now, this is when you have deterministic case. You could be like, okay, I don't care where I start. I could have 0.5 probability of starting at 1, 0.5 probability of starting at 2. So pi 0 could also be 0.5, 0.5. Okay, so now do you see that here your pi's are your expected number of times you are to visit state 1 and you are to visit state 2. Like the probability that you visit state 1 and probability that you visit state 2 at time t equal to 0. So now you want to calculate this for time t tends to infinity. That is what your steady state probabilities, or that is what your stationary probabilities. So how do you get, so let me call this as P, and then what you do is, so you want a solution for this kind of equation. So where you evolve, even if you evolve, you come back to the same. So evolution for a Markov chain is, okay, so let me give us very small example. Suppose I have 1, 2, okay, and yeah, so this is 1, and this is 1, and this is 0, this is 0, okay. So now I say pi 0 is 0.7, 0.3, P is 0, 1, 1, 0. Could you tell me what pi 1 is? So pi 1 is probability that you are at state 1 at time instant 1. Probability that you are at state 1 at time instant 1 is equal to the probability that you are at state 2 at time instant 2 into the probability of going from 2 to 1 plus probability that you are at time instant 1 into probability of going from. So I understand, I hope you understand the total of probability harmonics. Do you want me to write down those equations, every equation, or is it okay if I write it as a matrix notation?
Matrix is fine.
Matrix is fine. So
Yeah.
you could solve the matrix and tell me what pi1 is. This is actually very simple. Like you don't need to do even solve. So pi1 could be 0.3 comma 0.7. So pi1, this first term, how did I calculate it? So so it's probability. You are at state 2 at time t equal to 0 into probability of going from 2 to 1 plus probability that you are state 1 at time equal to 0 into probability 1 to 1. This is give you probability that you are at state 1 at time equal to 1. Do you see this?
Yes.
So probability state 2 into at time 0 is 0.3. I have given you already initial condition 0.3 into p21. Sorry, that is p22. p21 is this is p21 into 1 plus probability of state 1 at t equal to 0 is 0.7 into p11, that is 0. So you get 0.2. So now probability of state 1 at time equal to 1 is 0.3, and similarly probability of state 2 at time 1 is equal to probability of state 2 at time 0 into p22 plus probability of, so it's basically what you get is pi1 is equal to pi0 into p, pi2 is equal to pi1 into p. This is what you get, and you can write pi1 as pi0 into p, so pi2 is equal to pi0 into p square. This continues. So this is these are the basic Markov chain, no MDPs, only Markov chain definition. Now what do you mean by, okay, so what do you mean by stationary distribution is you want to go to a point where pi t is equal to pi t into p, like wherever it doesn't matter what was the probability that I was in state 1, it will remain same. Even if transition is also the probability that
Same.
so this
It
is
no longer changes.
I didn't get it.
It no longer changes. The
Yeah, it no longer
policy.
changes. Yes. It no longer changes. So this is the steady state distribution that you want to achieve in a Markov chain. Now I want to weight my errors while calculating the expected value function, linear value function, expected mean square error, weighted expected mean square error. I want to weigh it with these stationary distributions. But the main point that I want to stress is many Markov chains don't have stationary distributions. Could you give me the stationary distribution for this? Okay, so intuitively what happens is, so I'll tell the intuition behind this. So you started state 1 with probability 0.7. Since if you start at state 1, you will always, the next state will always be state 2. So if you start at state 1, then state 2, the next state will be state 2. So probability of state 1 is the probability of the next state being state 2. This transition matrix is designed like that. So there are some pathological cases of Markov chains where steady state distribution does not exist. This will just keep flipping. Pi2 would be 0.7, 0.3. Pi3 would be again 0.3, 0.7. They would just keep oscillating. You would never reach a steady state. Do you see that?
Yes.
So this was about Markov chains.
So instead of T, if we had an identity matrix, then we'd have a steady state distribution.
Yeah. Then you'd have a steady state distribution. But then any distribution you take would be a steady state. Like your initial distribution would be same. So even if you start at 0.7, 0.3, you would stay at 0.7, 0.3. If you start at 0.5, 0.3, you would stay at 0.5.
Yeah.
Yeah. So these are actually, there are minute technical terms they call this. So steady state distribution is the one where you tend to, right? Limit pi t tends to, as t tends to infinity.
Yes. Yes.
So limit pi t tends to infinity, pi where this tends, this is the steady state distribution. Okay. And pi t, this is anything which satisfies this is a stationary distribution. No, it's the invariant distribution. This is known as invariant distribution. So there are some cases where like there is a whole this thing on Markov chains being irreducible and reducible and all those stuff, and ergodic and all those stuff, where it says that not all Markov chains have a steady state distribution. And not all Markov chains have unique invariant distributions. So you need to make sure that when you formulate your MDP, every MDP underlying, okay, so you see that every underlying MDP has an is a Markov chain for some policy. Suppose you fix the policy, your whole MDP becomes a Markov chain.
Yes. Yes.
Because now you're going to pick actions based on that policy.
Yes.
That's it. Now the stochasticity remains only on the hand of the environment, so the environment does all the state shiftings. So you need to formulate your, when you formulate your MDP, you need to formulate it well such that you can have a what do you say? You have a steady state distribution, so that you can proceed to do weighted average for errors during weighted average errors. So this. So basically, what I'm doing is, okay. So my goal was to minimize theta, minimize in the space of thetas, expectation, summation. So one policy is fixed. So this is on policy. That is the main point. Okay, you also remember that everything I am doing here is on policy. So I fix one policy, and on that policy only I am doing it. If I change the policy, my Markov chain changes. If my Markov chain changes, the distribution changes. So everything is related. So everything I'm doing is on policy. So that is why every time I write V, I'm writing a V mu here. I hope that is also clear. Mu is the policy that I'm working on right now. So I was minimizing V mu s minus phi transpose theta. So this thing actually, what I can write is, I can write this as expectation of norm mu minus phi theta whole transpose this is, I'm writing the weighted mean square of where D is a diagonal matrix with entries in the diagonal as the steady state distribution. So what I'm doing is, for the first state, so I'll get so D. So now D is of the form pi 0 0 0 0 pi 1 0 0 0 pi 2, where pi 0 is the probability of being in state 0, like probability of state 0. Like probability that you are in state 0. Pi 1 is the probability that, okay, these are pi 0, pi 1, pi 2, these are not time indexed. Maybe I should have written it. This is the steady state. So maybe pi star, okay, pi star is the steady state distribution. This is pi star 1, pi star 0, pi star 1, pi star 2. So pi star 0 is probability that you will state 1, pi star 1 is probability that you will state 1, and so on. And here you'll have, there also you'll have a matrix where you have a vector where you have v mu first state, second state, third state, fourth state, first state, and it will be weighted by pi 0. The second state and second state will be weighted by pi 1. Third state and third state will be weighted by pi 1. I hope this is also clear. Or you guys have any doubts?
No, it's clear.
So the optimal, if you use least mean square error, and like if you okay, let's do that. So the optimal would be at phi transpose d phi whole inverse phi transpose d. The optimal theta. The optimal theta, I'm calling it as theta. So this. So now given a, okay, so yeah, so now for this problem which you are trying to do, the feature vector you know. So the feature vector you know. If you can model your this system as an MDP, and calculate the stationary distribution. So you have to model it as an MDP such that its steady state distribution exists or stationary distribution exists. Then you can write as a diagonal matrix. Phi you know, you calculate the whole inverse. Phi you know, d you know, some initial value function which you, okay, yeah, here the problem comes is you don't know the value function. So hence you do all the stochastic gradient approximation that sir has mentioned in class, right? And then you go back to, I hope I'm not confusing you.
It's not confusing.
Okay, so, okay, what is the problem with this? What is the problem with this? Doing simple linear approximation with this. I gave you an optimal solution. Can I do this? Okay, what am I trying to do here? What am I trying to do here? Or here?
Minimizing the loss.
Yeah, that is
But-
like, what is this? Yeah, but on a higher level, what am I trying to do? I'm trying to estimate something.
VS.
VS, you are trying to estimate the value function, right?
Optimal V function.
Not optimal, I'm just trying to find the V.
Okay.
If I do it Bellman multiple times, I'll reach to the optimal. But yeah, so yeah, I want to just parameterize all the V's. I don't know which is optimal yet. I just want to parameterize them V's so that given a theta, I can get any V. It need not be optimal. Once I get any V, I apply Bellman equation multiple times. I know that it will reach to my optimal. Right. So
Yes.
here the problem is I don't know what V is because I have parameterized V with some theta, and this is not a iterating equation, iterating update.
Yes.
So what in Sir's lecture what you see is you see that there is an update equation similar to what we did multiple times in the previous case also. I think in reinforce you did this, where you updated the parameterized thetas with theta t plus
Alpha times log
ln of
minus.
theta t into that error. That error term, I think, if you check sir's notes, it will come out to be RAT plus gamma at ST plus 1 equals to theta t minus at S. Sir uses some input phi of this.
Yeah.
So, okay, this no gradient. So this, why we are using this is main problem is because we don't know what we use, and we want to write this as an gradient descent or gradient descent problem.
Yes.
So sir gives all those stepwise where the data problem and all. Okay, so if you guys have any doubt in linear function approximation and why we are doing this and what are the necessary things when you model your MTP, like if you want to do your linear function approximation, you need to model your MTP in such a way that steady state distribution also exists. So I have that things and all that.
Yes.
Okay, so let me quickly go to the next thing. It's state aggregation.
So one thing I wanted to ask is, say if we are coming up with a problem and designing an MTP for it, and we want to avoid the obviously bad actions, like say when you're performing robotic surgery, instead of applying gentle pressure, you apply too much pressure, and so that's not needed, right?
Yeah,
So how do you?
Yeah, so that is actually a very good question. So actually, I know someone who is doing the same question again. So so this there are two philosophically reinforcement learning. There are two fields. Okay, so one is you have a simulation, right? You do multiple simulations. You don't implement it in the real world. First, you do multiple simulations. You do thousands and thousands of simulations. It learns what not to do. It itself comes with all the constraints what not to do. Once it has trained itself to death in the simulations, then you put it in the real world so that it doesn't apply much.
Right.
But there is another field of RL where you don't want it to run simulations. You directly want to implement it in the real world. Directly with some constraints. Yeah. So there is a whole field which is going on, which is known as constrained MTPs.
Okay.
You can maybe check it out. Constrained MTPs. So maybe I can. Constraint Markov process. Okay. Now I remember. There is book on Altman for constraint Markov process. There is also book on Kutterman, which has this constraint Markov process. But so constraint Markov process, what you are saying is where if you are at some state, then some states you are not allowed to do it. But those are valid states given those actions.
Right.
So and those are valid actions for the actuators, which, like the example that you said. So you want to perform a robotic surgery, you will have a robot arm which has to apply that much pressure if you are near a bone, because maybe it has to cut some bone or something, you have to apply that much pressure. But when doing surgery, the same robot, when it doing surgery on brain, it should apply the minimum pressure. So it's so those are known as constraint MTPs. So their main problem is, instead of simulating, so it comes under two things: doing what you are trying to do, and real time I want to run on. Or I want so it's not basically on that also. There might be some cases where doing something, doing something might affect the actuator also. So maybe you have an industry where you want to run RL or something, but doing that puts so much pressure on your instruments and equipments. They give you the maximum outcome, but they break those equipments into. You are out of the safety range, the safety range that you should be.
Right.
Yeah, so maybe that thing it doesn't learn because of you bad formulating of constraints and the pressure and wear and tear of the instruments. You can't simulate it because you don't have the full model. While simulation,
Yes.
it's like it can handle maximum pressure for how many amount of times you can do it. But once you put it in real world, maybe it can only handle the maximum pressure. Maybe you replacing that equipment is more like
Yeah.
it breaks after 1 week. I hope you
Mm.
understand what I'm talking about.
Yes. Yes.
Yeah. So that is a whole point on constraint MDPs. But that is how you define your MDP. Once you define your MDP, the rest follows.
Okay.
Yeah, you can look up this in Wunderman's book and
Okay.
but this is an active area of research. I would say that much. Like there are papers which give some good algorithms, but this is an active area of research.
Mm-hmm.
So that's a good question. So state aggregation. So state aggregation, basically, I'll just give the basic statement is suppose you have continuous state space. What you do is you divide it into bins, and then for all this bin you have one value function. For all this you have one value function. For all this you have one value function. For all this you have one value function. So this is how you handle continuous, which is a very bad way to handle, but this is what it does. Next there is tile-based aggregation, tile coding. So in tile coding, what you do is you have one tile with this. Then what you do is you shift. You shift your bins slightly to the right. So now, if you pick a state in this point, it belongs to the so a point here belongs to bin 2 in the blue bins and bin 1 for red bins. Two different value functions, you get better approximation of this small set. Now what you can do more is you can keep on shifting with small decrements, and you can take average of the value at that state is average of which bin it is located for which things. So as you shift with many times with small minute changes, you will see that you are basically evaluating the exact value function at that point. As the number of bins go to 10 to infinity, you are basically doing it continuous. But instead of infinity, you just do it for 5, 6, it's good enough. This is style-based coding. So this is just a workaround for how to work with continuous state spaces. Is this clear?
I'm sorry, can you explain the binning method again?
Okay, so when you have continuous state space, okay, so this may be line in continuous. So suppose you have continuous state space. So your state space is say some area. So your robot wants to go from here to here. Okay, so what you do is you make it you make bins. So each cell is one bin. Now instead of calculating the value function of all the points in that bin, you just calculate one value function for the whole.
Okay.
So every time every time robot enters this bin, calculate the value function. So first initialize value function all 0, 0, 0. It's similar to grid world, but grid world it was like robot could move one bin at a time. But in real world it doesn't move one bin at a time. It was continuously. So, but what you're trying to do is you're trying to imitate. So now you're trying not the inverse, but the reverse. I have the continuous state space. because I can't calculate the value function of all the states, I divide it into bins, and once the robot enters that bin, I calculate the value function, like whatever the robot gets there. So if it enters this bin, and all the time the value function of this bin is getting updated. Once it moves out of this bin, this updation of this value function will stop, and only this value function will be done.
So without the binning, the whole state space gets updated, is it?
Yeah, but without the binning, you don't that infinitely many points, continuous state space.
Right. So you're trying to bring some sort of discretization with binning.
Yeah, some discretization. Yeah. That is my initial goal with 1D, discretization, to show you discretization. Without that is what I went to 2D spaces to show discretization.
Okay.
That is the first one, binning. And now tile coding method is, what you do is you bin and then you shift those bins.
Okay.
Okay, so maybe let me try bit more small number of bits. So this is my, so what I'm doing is I'm doing another bin lines. I just shifted the bin, nothing else. These lines remain the same. Okay, maybe these also you can shift. These also you can shift down. Maybe a new thing. Now I shifted the bin a bit. So what happens is, suppose now you are in this point, your robot. You get a reward. So what all you are going to update? You are going to update the first bin in the red tile, first bin in the blue tile, first bin in the white tile. But suppose you are here, you are going to update first bin in the red tile, second bin in the blue tile, second bin in the white tile. But if you are here, first bin in the red tile, second bin in the blue tile, but first bin in the white tile.
Right.
Yeah, so the more shifting you do with more small discretizations, your as number of your shifting things goes to infinity, you are basically doing the finding the value function and continuous at each and every point that is that can be.
Yeah.
Because
So this has better results, but is computationally more complex
it's
than
computationally
the
more complex. So I want to show you a code where I did single tile at my laptops. Okay, maybe I'll stop sharing the link. Just tell me if you're able to see my screen up.
Not yet. Yeah, it's useful.
So this is a code that I've taken from somewhere and tried to run on my system. This is not for this is just a very simple mountain continuous state space where you have a car, you have a mountain, it needs to reach here. Okay, it starts from this point. If you use full acceleration from this point, it will reach maximum 80% and it will come back. It will never cross this because physical constraints. The acceleration doesn't allow it to go till here. So what it needs to learn is it needs to go back and then apply full acceleration so that it uses the gravity to go. So that is what it needs to do. It's very simple. What I've done is I've binned just one bin. So made a cube here. Not ISO, this is why I'll give you more. But in my system also this is taking too long to run because I have been running it for 1 hour and it's still going on. It's not so as you have said that computation is difficult for small end systems to run this. Yeah, so what I do is I'll in the description. Okay, this I have taken it from. So I'll show the video clip. You can see the video clip, right?
Yeah.
Yeah. So I've taken it from Sendex. So
Okay.
I'll link this in the description again. You can go for good codes. Maybe you can go to this codes. So even he runs into problems because of huge data.
Yeah, I've seen as Python plays GTF, I think.
Yeah. See, even now for his also, it's like not responding. So,
Right.
so yeah, he also runs into problems. And my laptop is not supporting.
Right.
I just wanted to show you this. So, okay, you missed that part. So,
Yeah. Right.
so maybe you looked up the link. But that I wanted to show that code because you can, I'll maybe put a link to his web page also when he uses this multivariate analysis. What he does is basically he continuous state space, he bins the continuous state space.
Okay.
So if you have a good system where you can get this to run, then maybe you can change the size of the bins. So, so yeah, this discrete OS size, these sizes you can change. You can change and you can see. This is only for one bin. I have not even this year. It's not even done the time coding where you shift the bins and then calculate. And then see that once you reach a state, what all the pins for different layers is active. And then you update the value function of all those pins.
Right. So one thing is we've learned that policy approximation, policy evaluation works better with continuous states, right? So where are we using V to value functions to do this?
No,
Yeah, instead
of Q, you're saying Q.
Yeah.
No, we are using Q. Q works better. You're correct.
Okay.
This is Q. You like you use Q. But okay, so let me tell you something. Okay, so the theory part, it's in, you can use V, you can use Q. No problem in using V or Q. I hope that is clear.
Yeah.
Okay, the next thing is showing convergence, rate of convergence on V is easy.
Okay.
Because you have an extra argument in Q, S.
Yeah. Right.
While doing code, what you do is there is an extra step where you greedily do it every time. That doesn't come into V. So showing theoretical stuff, convince rate of convergence is very easy on V.
Okay.
Once you show theoretical convergence and guarantee on V, you can just do that on Q by taking, by exploring on actions, action, being greedy. So Q learning and SARSA.
Okay.
So even in the continuous state space, doing bins, you can do Q learning, you can do SARSA, you can do policy iteration, you can do value iteration.
Right.
You can do anything. But then it depends on your computational power, your rate of convergence, what you V function is mainly for theoretical guarantee proofs. Q function is mainly for control in an environment, which is this thing. I think I when we were doing one of the tutorials, we were doing that deterministic settings. We did value iteration, we did policy iteration.
Yes.
Policy iteration, you know it has converged, so you can stop after 3 to 4 steps. But value iteration,
Yeah.
you know it has converged. We'll keep on going.
Yes.
Even when the greedy policy has converged. So
Yeah.
counter strike is right. Policy iteration is better than value iteration. But value iteration is easy to show. because you have computational power, it's easy to show that. Yeah.
Mm-hmm. So I've kind of read ahead and went into TQ a bit deeper, and I read the paper. One thing I couldn't understand in the paper was why they would use reward clipping.
They used.
Reward clipping. So basically, they changed all the rewards to plus in the range of +1 and -1. Anything greater than +1 will be +1,
Plus
and
one.
anything less than -1 will be -1.
Wait, could you? Okay, I'll stop my record. Could you send me the